So let's talk about molecular speeds. So molecular speeds, because we talked a little bit about this in terms of heat capacity and the sort of the microscopic properties of temperature and pressure. When we think about molecules, remember we have the cold molecules moving slower and the hot molecules moving faster, but they're not all moving the same speed, which is why we have to use the root mean square speed, because the molecules are kind of all doing their own thing. Generally, if one of them starts moving faster, it affects the ones around them. So on average, hot things have a bunch of molecules moving faster and cold things have molecules moving slower. But if you want to look at the actual distribution of speeds, this is molecular speeds, and here's the temperature, right? So this is your function over speed, and here's your temperature, and we'll talk about what the function means, but you can see for cold things, right, you have a narrower distribution of speeds, and for hot things, even though the average temperature is higher, you have a broader distribution of speeds. So even in a hot container of gas, you could have some very slow moving things close to zero and some very fast moving things, but the distribution is broader. So on average, they're all moving faster, and your fastest moving ones, there's going to be more of them, but you can see this is a distribution. So it's not a uniform thing, and this is why we look for the root mean square speed. Now, if you really want to dig into the super fun math of statistical mechanics, which is what the upper division thermodynamics class is called, you get to see a lot of fun equations like this, which start to look a lot like statistics. This basically looks like a Gaussian function where you have a constant and e to a like thing, a negative thing, and that's our envelope, right? So if you're thinking about math, this is just something e to the negative something, but it's a little bit more complicated because it creates this nice Gaussian distribution. If you know about Gaussians, you'll notice this looks very familiar. It's just got a bunch of little terms that make up the pieces. And this is called the Maxwell-Boltzmann distribution. And you could learn a lot more about this when you take either statistical physics or later like thermal stuff in engineering. The other thing about these molecular speeds is if you want to find your average speed, this is just sort of the fraction of molecules between these speeds. So you'd have to take an integral of the Maxwell-Boltzmann distribution to find what percentage of your molecules lie in that. Or you could just figure out the maximum speed, okay? All right, moving on to phases of matter. This is the pretty basic elementary school level. We have a gas, a liquid, and a solid, okay? So if you're thinking about water, that's steam and fluid and maybe an ice cube. Phase changes, we talked a little bit about in terms of calorimetry. But remember, we have a solid, right? And then you can raise the temperature to reach the melting point. So if you're talking about ice, you're raising it to 0 degrees, and then it starts to melt. It transitions from a solid to a liquid, then it's a liquid, then you bring it up to boiling temperature, that's going to be 100 degrees, and then it starts to evaporate or turn into vapor. So that's a transition. And you'll notice the temperature doesn't go up during the transitions, it's flat, right? So while you're transitioning from a liquid to a vapor, you're not changing temperature. Both your liquid and your vapor are at about 100 degrees Celsius in this case. And then as you have a gas, then you can change the temperature once it's evaporated. So really, we have these transition points, and you can go backwards up and down this thing, right? So you have temperature change, and then phase change, and then temperature change, and then phase change, and then temperature change. But while you're changing phase, you do not change temperature. So overall, for these phases of matter, it's a little bit more complicated than just the water. You also have to take into account pressure and temperature. Now, we've been talking a lot about pressure volume diagrams, but this is a pressure temperature diagram. And this is something you definitely go over in chemistry. So here would be our solid state, our liquid state, and our gas state. And so depending on what your pressure is, you can see if you draw horizontal lines across this, you can see what your phase transitions are going to be. So the graph we looked at previously, really you're cutting across, like if you put a horizontal line across the middle and hold the pressure constant and just change the temperature, that's what you're getting. But this graph includes both the pressure and the temperature. So yeah, here's our various pressures that we could have. And then here's various like fixed temperatures. You can see depending on what your temperatures and pressures are, like you can see here's pressure critical and temperature critical. They go through the critical point. You can get different situations. So for instance, if you make the pressure low enough, you can go directly from a solid to a gas, and that's called sublimation, okay? And these triple points the triple point is a temperature and a pressure where you can have all three states in the same, all three phases at the same point, okay? So you could have like steam, liquid water, and ice if you got the temperature and pressure right. Okay. So here's our phase. This is the phase diagram for water. You can see here's our triple point. Here's our critical point. Here's where it's a solid. Here's where it's a liquid, and here's where it's a gas. And this is at 218 atmospheres. You can hit this critical point. You can hit the triple point at 0.006 atmospheres. And here's the temperature at which you reach the critical point. But generally, here's our 0 and 100 down on the bottom. So you can see if you're at 1 atmosphere, you cross this phase transition at 0 degrees and at 100 degrees. So that's where we find our boiling and freezing points. So here's a question, and I want you to think about this and then vote. Okay, so the highest temperature at which ice can exist, well, you look for the maximum on the freezing point, and that would be at 0.01 Celsius. That's where the triple point is, so that's where you can have a solid, liquid, and a gas. Okay, so this is the next one. What's the lowest temperature at which liquid carbon dioxide can exist? So try this out. Okay, and that's going to be 56 degrees Celsius because remember, liquid CO2 has to happen, the lowest possible temperature in that area happens to lie on -56. So that's also at the triple point going the other way. Okay, so here's one last question. At high altitudes, boiling your water is not always a safe way to purify your water. And why is this? That's right. Since we have changed the pressure, water is going to boil at a lower temperature, which is fine, except that some of the bacteria and microbes you're trying to kill need a higher temperature in order to die. So the water starts to boil off and it doesn't kill your bacteria and microbes, so you still get to consume them, and then you get sick and maybe die in the wilderness. So that sucks. So keep in mind, when you're up at higher altitudes, you might need to change your biology practices as far as your potable water. Potable water? I don't know. Oh, there's one more. So, for which of these is there a sublimation temperature that is higher than a melting temperature? And that's going to be for water, because you can see there is a place if you change, because that line between solid and liquid is not flat, right? It's got a slight slope. You can get sublimation at around 0.01 degrees Celsius, even though you can get, if you have a higher pressure, you can get melting instead. So we've looked at our P versus V, our PV diagrams. We've looked at pressure temperature diagrams. And overall, if you want to look at this, you can plot all of these state variables, pressure, volume, and temperature, onto a three-dimensional surface. So just so you know this is there, these can be plotted out, and you just take slices of them so you can see, you fix the volume and then you get pressure versus temperature, or you can fix the temperature and you can get pressure versus volume. So here's the sort of pressure versus temperature versus volume surface. And you can see this is for a more ideal situation where we're talking about an ideal gas. And you can see all the constant pressure, constant temperature, and constant volume plotted onto the three-dimensional space.